Right. So about 6 months ago, I got an email from Charlie D. Cook, and he invited me to give a talk here, and of course I was honored, but I had to tell him, we pivoted from a hip company, which we started out as, to a knee company. And I couldn't help but notice that the word hip was in the name of the conference. So, but he said, no, knees are fine, knees are great. And then in a kind of a classic bait and switch, a couple months after that, I get an email saying, maybe you could throw some hip in there too. So, I had to go into the vault and dust off some slides. But I bring that up not to break his chops, but to make the point and kind of emphasize one of the points that Charlie made in his great talk, which is that when you innovate, there's this kind of constant tension between staying true to your vision and dealing with reality. And you just never know when you need to kind of pivot. So hopefully we made the right move and pivoted to knees. That's what the market was kind of telling us that it wanted, but certainly hips are in our future. So a few years ago, I'm in the OR watching one of my residents do a femur, and it's just the implant's just not going to fit right. We had to ream the canal. It was pivot. It was potted distally. We had to open the canal up. Then we cracked the calcar, and I said, "Geez, there's got to be a better way to do this." He was happy with himself because he got the thing to work, but maybe we could do better. So a few years after that, my son's working on a school project, and he showed me this. I thought it was so cool. These archaeologists are basically taking at-risk archaeological treasures. They're scanning them, and then they can use robots or 3D printers to essentially remake these irreplaceable archaeological things. So it made me think, look at what robotics are doing in our operating rooms, and look at what they can do here. And that's a lot more complex than what we're asking robots to do in our operating rooms. So maybe we can kind of get more out of robots in the OR. And so I started to think about, well, what if you had an AI-generated model of the bone that had the cortical dimension, the inner cortical dimensions and shapes, the geometry, the thickness, even stiffness of the bone. And then you had the ability with a robot to mill any cavity in any bone that you wanted with sub-millimeter accuracy. And then you could print anything you want with titanium alloy in 12 hours with some post-processing after that to fill that cavity. If you had those tools at your disposal, would you imagine implants the way they've been for the last few decades, or would you think of something different that was unconstrained by inventory or manual instruments that we have? Would you reimagine the implants? And that's kind of where we're going as a company. This is actually a little stem that in the early days of Monogram, I actually manually drew a sketch of this stem based on a CT scan that I had it 3D printed in Munich, where I was at a conference, and it was delivered to my hotel room within 12 hours of me sending them the digital file. So I thought that was just super cool. This stem could not be put in. I've learned a lot since I did this manually. This is just a flail, but it's interesting what you can translate into a metal part. So this is the way our platform works. We start with a CT scan for now. We create that 3D map. Our AI algorithms are extremely accurate. And then we take that map, we develop an implant that is highly conforming with a high degree of cortical contact, restoration of anatomy, and then the robot mills that cavity. This is our kind of goofy promo videos with the smoke machine. So that's our robot. And I'm not standing up here telling you we figured out what the implant should be. What I'm trying to make the point is that we can maybe rethink them and do all kinds of different things with some new tools that we're going to have at our disposal. So the stem that we designed was very short, like I said, designed for a high amount of cortical contact to restore the native anatomy in 3 dimensions. And it has to be, this is interesting, it has to be, because it's so conforming to the bone, we needed software to ensure that the cavity was millable and that the implant was insertable. Because if you make it, just because it fits the bone perfectly doesn't mean you can get it in there. So that's kind of part of our IP is being able to mill the cavity and making an implant that you can get in there. So we tested this hypothesis that if we had a stem with a high amount of cortical contact, it would be more stable than stuff that's on the market now. And sure enough, this is a study we did at UCLA, a micromotion study. And sure enough, we found that we had about 9 times the cortical contact of a conventional off-the-shelf stem, which translated into over 600% better stability. They basically looked like they had been cemented in there. And then we looked at how well we restored the center of rotation of the femoral head. I had one of my colleagues template 10 specimens and do the best job he could to restore the native anatomy. And he was off by 1.4 centimeters if you add both planes, compared to the Monogram hip, which nailed it. So whether or not you want to restore the native head center is a separate question. But the fact is, if you tell it to go there, it's going to put it there. So this is a video that we were sent by a testing lab. They tried to jazz it up with some cool fonts and this music to make it more exciting, but it's really just a stem sitting in some water, getting fatigue tested. But what we were able to find, because the concern with 3D printed hip stems is the amount of fatigue stress. Are they going to break? Because they're just, traditionally have not been as strong yet as a forged implant. But we were able to develop a process using a proprietary powder and some post-processing that we were actually able to pass the 2 primary FDA tests for stem fatigue. So that was pretty exciting, as shown in that video there. So, but then after we did all this work, the market, we were raising money, we needed to kind of be interesting to strategics. We needed to raise money. So we pivoted to become a knee company, which was hard for me because I felt like they were calling my baby ugly, but we had to do it. That's where the market was going. And so we looked at, a bunch of issues with hip stems, and then when we pivoted to knees, we said, well, what can we solve with the knee? Things seem to be going to press fit, uncemented knees like they were with hips a few decades ago. So can we improve the fixation by customizing the implant, by making something a little bit funkier than a flat stemmed, implant that we've been putting in for years? So we developed this funky little humped, finned thing that we can, as you see, can mill out. You can't do that with a saw. And kind of looks crazy. And again, I'm not telling you this is the final answer, but when we tested the stability compared to leading press fit implants that are commercially available, we found, again, really kind of dramatic improvement in stability, almost 300% more stable under gait analysis load. This is kind of a more detailed view. So now I'm going to pivot back to knees. That's all I got on hips. I found every slide I could. So this is where we are with knees right now. So we're using AI to register the bone. We're trying to speed up robot use in the operating room, starting with registration. So we have an AR camera. We don't have goggles, but we use an AR visual light camera. So it's an active robot, so there's no haptics. It's a foot pedal controlled, hands-free robot. We are optimizing the cut paths. We're actually currently studying how the saw most efficiently goes through the cuts. And it's amazing how you can tweak that to make the cuts more efficient. And we think that we can get both of the bone cuts on a knee down to about 2 minutes. We're at about 4 right now. But with optimizations, with improving our motor and our blade, we think that we can even do better than that. So again, we want this to be able to mill and saw. The saw is good for speed, the mill is good for custom. So we developed a quick change device that'll allow you to sterilely go between different tools, a saw, a burr, a reamer if you were doing an acetabulum, but it's a very quick change, sterile change. And this is a cavity that we made for a custom knee. We're also using our AI in knees to help position the implants. You don't necessarily have as good exposure with the robotic knee as you might with a manual. So having some help with making sure that the implants are where you planned them, we think we can use AI for that purpose. So, I'm not going to tell you that everybody needs a custom joint, and we certainly are not naive to that. There are lots of reasons that everybody doesn't need a custom joint. So we're starting with a fairly conventional press fit implant that we licensed. Our Gen 2 implant will be more amenable to robotic milling, and then we'll go into true custom as an option down the road. It's just impractical from FDA clearance standpoint to try to clear a custom implant and a robot at the same time. That's just too big of a steak for them to eat. So, we view this as a platform technology. Our robot is extremely versatile. It's a 7-degree of freedom arm. It's very robust. It can do things that most other robots out there just can't in terms of versatility. So we're starting with knees. We'll go to Unis next. Hips is near dear to my heart, so that'll be our next. But shoulders, ankles, kind of sky's the limit with this robot and with the ability to change instruments. So with that, I'll open it up for questions if anybody has any. Thanks.
While people are walking up to ask questions, just a quick question for you. You mentioned the role of sort of FDA approval, we'll just say regulation, right,
yep,
in your design and development process. How influential is that on ideas as you're coming up with innovative next steps to say, it's going to be really hard to push this through from a regulation standpoint, so maybe we should pivot and think about it this way?
It's very influential. I mean, so the two things. One is the regulatory stuff. We just can't have stuff that's too far out there, and also just the 3D printing aspect where you have to worry about fatigue strength and mechanical properties. You just need to make sure it's going to be as good as traditionally manufactured stuff. But yeah, and that's why we kind of decoupled the implant and the robot, because it's a lot to get it all through in one bite. So, Stefan.
Great presentation, and had an interesting discussion earlier with some people about accuracy. And currently, we get robotics gets compared to navigation, and navigation is a standalone system that has its accuracy. When you look at what you're doing is you have a CAT scan, you have a segmentation, auto segmentation, then you have planning, and then you have navigation execution with an autonomous robot. My question to you is, should we redefine the standard of what accuracy and precision is with all these new robotic platforms? Because if you claim you're accurate, you have to publish your accuracy data of the system, not just the accuracy of the robot. And I'd love to get your input, being in the autonomous robot world, and you've been in it longer than anyone because I know you work with things surgical. I'd love to get your opinion of how should we define accuracy, how should it be measured, and should there be a new standard?
Yeah, well, I mean, certainly you look at the whole system. So you've got to look at the implant, the cameras, the registration, and there's kind of a stacking phenomenon that you get. Every part of the chain where there's error adds up, and the final total is kind of how accurate you are. And so you have to kind of measure each. I mean, I don't know if this answers your question, but I think it's, you know, you have to measure each component along the way. That's one part of it, you know, because you are evaluating the whole system. So you've got to look at the camera accuracy. What's just the inherent camera accuracy? What's your registration algorithm accuracy? What's your segmentation, auto-segmentation accuracy? So, you know, yeah, I think you have to basically look at each critical step and add those up and get to what the, you know, how accurate you are. Now, as far as like what number that is, I don't know. But I think that you have to be able to do essentially what you say you can do. I mean, that's where we are right now, is in what's called V&V, validation and verification, where we're just running test after test to internally say, is this thing doing what we say it is? Is it putting it where we say it is? So.
I know we're running short on time, so just a quick question. And it has more to do with the customization of implants. So as I understand your platform, you use a CT scan and then use your technology based on the patient's native anatomy. And how do you equalize that in the many, many patients that we have that have deformity as their native anatomy, and that we currently use our implants to try to correct? Yeah.
So you're really looking at the, you know, we're kind of focused on fixation and kind of the bony contact that press-fit implants have, whether it's a hip or a knee. So we're really looking at kind of the intercortical anatomy, which is going to be, you know, less of an issue as far as deformity goes. I mean, it certainly is an issue, but you know, so as far as the kind of surface anatomy, that's really not in play there. Anything else?
All right, great, thank you.
Thanks.